Hello students, and welcome to our first video lesson for starting 10.5 entitled Testing Convergence at Endpoints. So I'm using a microphone, so hopefully the audio is better in this one. Please let me know if you have any issues. Experience it throughout the lesson here, and I can try to make adaptations for the future. But I got it set up here in my basement, and hopefully this works well because we're probably doing this the rest of the year. So anyways, testing convergence endpoints, as I said. Going back to 10.4, we were finding the radius of convergence. So given a center, we can go R in either direction. From there, we can find an interval of convergence. But before we complete the interval, we have to test the endpoints to see whether or not converges those endpoints. Now, before we do that, there's a couple new tests we're going to learn. So the endpoints comes later. That'll be part 2 of the lesson. Today, we're going to talk about a new test called the integral test, which gives us something called a p-series. So, to begin here, and if you have your book open to 523, you can look. The integral test is used in certain conditions, but what we're going to do is compare the series, the infinite series, to an improper integral that we studied before. Okay? And if we can find out whether the improper integral converges or diverges, then that can tell us whether the series converges or diverges. And once again, it may not converge to the same number, but I don't care about that. I just want to know, does it converge or does it diverge? Okay? So if you go to your 10.5 handout, here's when the conditions it must be true to use the integral test. Okay. It has to have a sequence of positive terms. All right. It has to be continuous, positive, and decreasing function of x for all x greater than or equal to n, where n is some positive integer. So what that means again is at some point, not necessarily at the beginning, but at some point after some capital N, the function has to be continuous, positive, and decreasing. We have to show or state that that's true before we can use the integral test. And if that's true, then this infinite series and this improper integral either both converge or they both diverge. So if I can use what I know about improper integrals, which we studied before, to find whether this integral converges or diverges, that will tell us whether this series converges or diverges. Okay? But again, you have to first show that it's continuous, positive, and decreasing. Okay? The continuous and positive part shouldn't be hard. The decreasing is sometimes we have to do a little bit of work. All right. So let's begin example 1 here. Determine the convergence or divergence of this series. Sum of 1 over n times the square root of n. Okay. So we want to compare it to a function. All right. Just basically replace the n's with x's and call it 1 over x times the square root of x. Okay. Which that could be simplified, of course, as x to the 3 halves. Right? Because when you multiply bases, you add the exponents. Okay. Or even further, x to the negative 3 halves. All right. So I have to show that this is continuous, positive, and decreasing for some number greater than or equal to 1, since it's starting at 1. Okay. Well, this has a discontinuity at 0, so it's continuous from 1 to infinity. That's pretty clear. And again, as long as x is positive, this will be positive, so the positive is clear. So the only thing I really have to show is the third part, the decreasing. Okay. And how do I show that a function is decreasing? If you show its derivative is negative, right? We know that from last year, right? If a first derivative of a function is negative, that function is decreasing on the interval. So let me go ahead and quickly take the derivative. That would be negative 3 halves x to the negative 5 halves, right? And as long as x is positive, which it is, right, because we're going from 1 to infinity, then a positive number, then this would be positive, and then times negative 3 halves will be negative. So this would be negative for all x greater than or equal to 1. And again, the reason I'm starting at 1 is because my series starts at n equals 1. All right, so I've shown that that's true. So that was just the first part. That was just the conditions to allow me to take the integral test. Okay, so now I want to find this improper integral. The integral from 1 to infinity of x to the negative 3 halves dx. Again, if this integral converges, then this series converges. If this integral diverges, then this series diverges. So remember back to improper integrals, we replace the infinity sign with the letter b, and then we take the limit as b goes to infinity of the integral from 1 to b of x to negative 3 halves dx. All right, so let's do the antiderivative. Add 1 would be negative 1 half, multiply reciprocal, so it's going to be negative 2, x to negative 1 half, plug in b and plug in 1. And so we have the limit as b goes to infinity of negative 2 over radical b plus 2 over radical 1, which is just 2. Okay, and as b goes to infinity, we know as the denominator gets large, the whole fraction gets small, so this approaches 0, so this converges to 2. Okay, so this integral converges. Right? Since the integral converges by the integral test, then the series converges. So let me go over here where I have room, put my dot, dot, dot. Then the series from n equals 1 to infinity of 1 over n radical n converges as well. Okay, so that is my conclusion by the integral test. All right. Now, the integral test is useful for problems that look like this, where you have a 1 over n to a power. Integral looks like, so again, you have sum from 1 over n to the p, where p is a constant. So anytime we have a sum of a constant, actually it doesn't have to be 1, any constant, over n to a power, where p is a constant, that's what we call a p-series. That's what we call a p-series. Okay. So there's a rule we're going to learn here in a moment that tells us whether or not a p-series converges or diverges. So you don't have to use the integral test every time to show that. Okay. You could prove it, but once you know the rules here, you don't have to use the integral test every time. Okay. So this p-series is an important one to know. Like if you remember back to 10.4, we were doing a comparison test. We took a series we didn't know and we compared it to a series we did know, right? Right now, the only series we know basically are the geometric, besides the other like e to the x inside a cosine. But just in general, we know a geometric series, okay? Now, we can also compare a series, if it doesn't look geometric, we can compare it to a p-series, okay? So this is going to be very, very useful for us in the future to compare unknown series to a p-series if it's not geometric. So, again, here's what a p-series looks like. It's a sum from 1 over n to the p. Okay. And again, you could really have any constant on top because we know if there's a constant on top, that's just multiplication I can bring out in front. It's not going to change the convergence or divergence. So 1 over n to a p. Okay. So like 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, where p is any constant. Okay. Here's the rules. It converges if that p is greater than 1. It diverges if p is between 0 and 1, including 1. So if p is 1 or below, it diverges. If p is greater than 1, it converges. Now, the series with p equals 1, which is this series right here, sum 1 over n, okay, that's called the harmonic series. It's a harmonic series. It's used so often it's given a special name, the harmonic series, okay. It's the most famous divergent series in mathematics. So this diverges because if you look, 1 over n would just be p equals 1. So it diverges. But notice, it's the bound. It's the bound of divergence, okay? If you make this p a little bit bigger than 1, it converges, right? So if you have 1 over n to the 1.00001, it converges, okay? But if you have 1 over n, then it diverges. So it's sort of the bound between convergence and divergence, if you will, all right? And so it's called the harmonic series. Again, so we're going to use this a lot. We're going to use comparison tests, compare it to 1 over n, because we know that diverges. All right. And if you're interested where that word harmonic comes from, there's a little bit extra in your book on the side of page 524. All right. When you hear harmony, harmonic, you think of music, harmony and music, and that actually comes from the same root. That's where the term harmonic comes from. It has to do with the notes on a vibrating string. So those of you in music might want to look at that connection between math and music there. So anyways, on to the next page. So now we basically, as I said, to repeat myself, we have two types of series that I can look at and know whether they converge or diverge. A geometric series and a p-series. Okay, and I can do a comparison test to one of those. Now, previously, the comparison I did was the direct comparison test. That was from 10.4, where we set up an inequality and compared one we didn't know to a series we did know. Okay, remember, for the direct comparison test, inequality had to go the correct way. All right. Actually, hold on a second. Let me do a quick. Let me just do on the top here. Let me just remind you here. The direct comparison test. All right. Give a second to focus. So remember, for the direct comparison test, we compared, two series of A sub n and then a series of B sub n. Okay. And if we showed that A sub n was always less than B sub n, if B sub n converged, then A sub n must converge. Or if A sub n diverged, then B sub n must diverge. Right? Remember, the comparison only worked one way. If B sub n diverged, we didn't know about A sub n. Or if A sub n converged, we didn't know about B sub n. Okay. Well, if you cannot use the direct comparison test, another test you can do then is a limit comparison test. So it's a second comparison test. If the inequality doesn't work for the direct comparison test, then you can use a limit comparison test. All right. So here are the rules for this. We're going to compare again two series, A sub n and B sub n. One that we know whether or not it converges, and the other one we don't know. So we're going to do the limit as A sub n over B sub n. It doesn't matter which one's on top. If that limit is any non-zero constant, then the series of A sub n, the sum of B sub n, either both converge or both diverge. Okay, so as long as this is any non-zero constant, any number, then they either both converge or both diverge. If the series is 0 and B sub n converges, then A sub n converges. And third case, if the limit is infinity and B sub n diverges, then A sub n diverges. So once again, for these two, they only work in certain ways, right? If you get 0 and B sub n diverges, then we don't know. If you get infinity and B sub n converges, we don't know. But if one of these two happens, then we can follow those. But most of the time, it'll be this. You'll get some non-zero constant, and then we can say, all right, whatever happens to A sub n happens to B sub n. All right, so we're going to do 3 examples here for part 3. We're going to give you a series and determine whether this series converges or diverges. So what we want to do is we want to find a series to compare it with, okay, and then use our limit comparison test. All right, so I'm going to go ahead actually and skip to a different piece of paper just to give myself enough room. I know I have all 3 in one page there on your paper, and it's kind of crammed in. I just try to save space. It's kind of crammed in there. So you can write it down in there if you want, or if you have more room in the sheet of paper, if you want to do it, that's well. Okay. So I'm going to do example 3, A, B, and C, and then we're going to stop for today. All right. So basically, we have to do 3 things. Kind of like with the direct comparison test, right? First, we found a series to compare it to and showed the inequality. Secondly, we stated what happens to the one we compared it to. And then third, we stated, all right, we would give our conclusion because, A sub n converged, B sub n converged, or vice versa, whatever it was. Okay. So likewise here, we want to do 3 steps. Okay. Step 1, we have to find something to compare it to. We want to do a comparison test. And we always want to compare it to something we already know. And as I said before, now we have 2 series to compare it to. We can compare it to a geometric series or to a p-series. Okay. So, what you want to do is you want to look at the terms inside. We want to ask yourself, what happens as n goes infinity? With all these things, that's all we're asking about is what happens as n gets large. I know what happens at the beginning. I want to know what happens as n goes infinity. All right. So, as n approaches infinity, what happens to these terms? 2n plus 1 over n plus 1 squared. Okay. What does that look like? Okay. Well, of course, as n goes infinity, the plus 1 doesn't really matter, and this plus 1 doesn't really matter, right? We just always look at the highest degree. So this is going to look like 2n over n squared, okay? What does that reduce to? Well, the n's cancel out. That looks like 2 over n, okay? And, well, what does that look like? Well, take out the 2, and it's 1 over n, all right? So the sum from n equals 1 to infinity of 2 over n is just 2 times the sum of 1 over n. And I'm just going to use the sigmas. I'm not going to write the 1 to infinity just to save some time. It looks like 2 times sum of 1 over n. But what do we know about this? This thing diverges, right? That's the harmonic series. That's a p series with p equals 1. That's a harmonic series. That thing diverges. Okay, so I'm going to take this series I don't know and now compare it to this series, 2 over n, or 1 over n. It really doesn't matter which one you compare it to. Again, but we're going to compare the series we don't know to 1 over n, the series we do know. All right, and since this diverges, as long as the limit is any non-zero number, this will always diverge. Okay, so step 1, we found a series to compare it to. Step 2, now we're going to use the limit comparison test. So we're going to take the limit as n approaches infinity of a sub n over b sub n. So again, you're taking this series we don't know, compare it to this series we do know. So 2n plus 1 over n plus 1 squared divided by 1 over n. All right, so as always, dividing by a fraction is the same as multiplying by a reciprocal. So 2n plus 1 over n plus 1 squared times n over 1. Okay, well, what happens as n goes to infinity? Just like before, we look at the degrees. N times 2n would be 2n squared. 1 times n squared would be n squared. So this thing looks like 2n squared over n squared. Since the degrees are the same, look at the leading coefficient. This whole thing approaches 2. I hope that should be clear by now. So, and since we got a non-zero constant, so again, to remind you, limit comparison test, right? If we do the limit of a sub n over b sub n, as long as we get some non-zero constant, whatever happens to a sub n happens to b sub n, or vice versa. Okay. Well, so I took this series I didn't know, compared to 1 over n. Okay. But since this series diverges, then by the limit comparison test, this series must also diverge. So that's our step 3, to state the final, conclusion. Okay. You can say the limit. Not the limit. Excuse me. The sum from n equals 1 to infinity of 2n plus 1 over n plus 1 squared diverges by the limit comparison test. Okay, so to recap, you're given a series we don't know. We want to find a series to compare it to. So say like, what does this look like when n gets really, really big? This looks like 2 over n or 1 over n. And then state what happens to 1 over n. Well, this series diverges. Do your limit comparison test, take this limit as n approaches infinity, show it equals any non-zero constant. And then because this original series diverges, then the series you compare it to diverges. All right, that was our first example. Okay. Let's do another one here. Okay. 1 plus 1/3 plus 1/7 plus 1/15. The series is 1 over 2 to the n minus 1. Okay, so what's going to happen here? As n goes infinity, what does this look like? Well, pretty clearly, we can take away the minus 1, right? And it just looks like 1 over 2 to the n, which is the same as 1/2 to the n. Hey, that's a geometric series, right? That's a geometric series, but r is less than 1, so it converges. So, because r is less than 1. Because r is less than 1. So it's a geometric series. Just to be clear. All right, so step 2. Now I'm going to do my limit comparison test. I'm going to take the limit as n approaches infinity. 1 over 2 to the n minus 1 over 1 over 2 to the n. Okay, well, we write it as multiplying by reciprocal. So 1 over 2 to the n minus 1 times 2 to the n. Okay, what's going to happen as n goes infinity? The minus 1 doesn't matter. 2 to the n over 2 to the n approach 1. Okay, and kind of like we talked about before, technically you'd have to use L'Hopital's rule to prove that, but you don't have to do that, as long as you just know that 2 to the n over 2 to the n reduces to 1, because the minus 1 here doesn't matter. All right, so there we go. There's my limit comparison test. So then our conclusion then is that the original series, 1 over 2 to the n minus 1, converges by the limit comparison test. Okay, so let me go back to the beginning for a moment. You might be saying, well, could I have used a direct comparison test, the one we did previously? Well, let's see. I would need to set up an inequality between this series and this series. Okay, well, which one is bigger? Well, since I subtract one, that means that the denominator is larger, which means that the whole, or sorry, I said it backwards, sorry. I subtract one, the denominator is smaller, which means the whole fraction is larger. So this is bigger than this, okay? So since this series converges, then that wouldn't tell me whether this converges or diverges, okay? So there's a small difference here. If that were a plus one, making this less than this, then you could have used the direct comparison test. But because it's a minus one, making this greater than this, then the direct comparison test wouldn't work. We had to use the limit comparison test, okay? So as you can see nicely about the limit comparison test, it doesn't matter which side is greater than or less than. You can, either way the inequality goes, you get the same answer. All right. So hopefully after you you see that the limit comparison test isn't that hard to do. It's just kind of making sure you write out everything that you're doing and showing what it all means. Okay. Last one here, example C. As we want to compare this to something. All right. Through the sum from 2 to infinity, 3n plus 2 over n cubed minus 2n. All right. So as always, say what's going to happen to this as n goes to infinity. So 3n plus 2 over n cubed minus 2n looks like what? Well, just look at the highest degree. It looks like 3n over n squared. Cancel out n cubed. Sorry, 3n over n cubed. Cancel out the n's, and it's 3 over n squared. Okay. Which is basically the same as 1 over n squared. And what happens to 1 over n squared? That's a p series again, right? 1 over n to the p. That's a p series. But this time the p is 2. Since 2 is bigger than 1, it converges. Okay, so let's write that out. The sum from n equals 2 to infinity of 1 over n squared converges because it's a p series with p is 2, which is bigger than 1. Okay, so we found something to compare it to, a p series that converges. All right, step 2, do my limit comparison test. Limit as n approaches infinity. Okay, so we're going to compare this to this. So we're going to start out, and I'm going to once again skip right ahead to the second step. Instead of showing the division, I'm just going to multiply by the reciprocal. So this divided by this is this times n squared over 1. Okay. What's going to happen here? Well, multiply by n squared. I have 3n cubed over n cubed. Since the degrees are the same, look at the leading coefficient. That thing approaches 3. Hey, that's a non-zero constant. So what does that mean? Well, since the series I compared it to converges, that means my original series converges. So this series, 3n plus 2 over n cubed minus 2n converges by the limit comparison test. All right. So that's 3 examples of using the limit comparison test. All right. So now we have 2 different comparison tests we can use in summary. We can use the direct comparison test, or we can use the limit comparison test. All right. And we have 2 series we can compare these to. We can compare them to a geometric series, or we can compare it to a p series. Okay. So basically with the direct comparison test, the inequality has to work the correct way. All right. The limit comparison test doesn't matter which way the inequality works. Okay. But this one, if it works, is probably easier because you don't have to take a limit. You can just show that A is less than B or vice versa. And that's all you have to write. Here you actually have to evaluate the limit to show that this works. Okay. So I'm going to give you a homework assignment now. Give me a second here. And let me I want to kind of walk you through some of the problems to help you get started from 10.5. So look at page 534 of your book. All right. And I am going to give you 5 and 6, and then all, then 7 to 17 odd. 5 to 6 and 7 to 17 odd. Okay, so let's look at those. I want to kind of help you get started. 5 and 6, it wants you to use the limit comparison test. Determine whether that series converges or diverges. Okay, so again, look at those. It should be pretty clear right away what series to compare it to, either a p-series or a geometric series. All right, and then 7 through 17. Determine whether the series converges or diverges. Just like before, there could be more than one way to determine that. All right, remember, the first thing to always check is the nth term test, right? Check that the terms themselves go to 0. If they don't go to 0, then automatically it diverges. Okay. Now most of the time, they will go to 0. Okay. But there may be one in there where it does not. Okay. And that's something you shouldn't have to write out. You can just sort of look at that and do it in your head, hopefully. And then, all right. If the terms go to 0, then what do we do? Well, then look at this series and say, okay, what does it look like? You know, like for number 7, take away the plus 1. Looks like 5 over n, which looks like 1 over n, which is a divergent p-series. So then you have to say, all right, it's n plus 1. So how does that compare to 5 over n? Well, since the denominator is larger, that means that the whole fraction is smaller. But since 1 over n diverges, and 5 over n diverges, then that inequality isn't going to help us. So you can't use a direct comparison test. You have to use a limit comparison test. Right? Some of these you can use either. Some of these you can use a direct comparison test or a limit comparison test. Okay. Let me skip ahead to number 13. All right. This one you want to rewrite as if we did these before, if you remember. Sine 1 over n times n. You want to move that n to the denominator to write it as 1 over n in the denominator. And then you want to find the limit as n approaches infinity. All right. This is the one that's going to fail the nth term test. The terms don't go to 0. But to show that, you have to use L'Hopital's rule. So I want to see you all write that out for number 13. Bring the n to the denominator, write it as 1 over n, then use L'Hopital's rule on that. And if you remember, what happens is you're going to do the chain rule, and some of the derivatives will cancel out, and you can finish it from there. So try that for 13. Use the L'Hopital's rule to show that the terms themselves don't go to 0. So this one fails the nth term test. The rest of them, you have to use either the direct comparison test or the limit comparison test. Okay, so that is the end of that lesson for today. All right, so work on those homework problems and let me know through the message board on Google Classroom, or send me an email if you have any questions. All right, and I can post some solutions tomorrow. I can work out any problems you have questions with tomorrow. All right, thank you, everybody. Have fun.